Hello. The purpose of videos 2 and 3 will be to present how to take matrices and do basic algebraic operations like addition, subtraction, multiplication, division, things that we'll be using for our application of matrix algebra in the lecture and class. So addition is the first one, and in addition to add to a matrices, one of the things that is a requirement or a basic assumption is that they have to have the same dimensions. So you can add a 2 by 2 matrix with another 2 by 2 matrix, or a 2 by 3 matrix with a 2 by 3, but you can't add a 2 by 2 with a 2 by 4. Addition is done by summing the same elements from each matrix, and it results in the final matrix. So if you add A11, which is 3, to B11, which is 4, what it will result in is C11, which is 7. Let's try another one, where if we take A22, which is -3, we add it to B22, that's going to be 10. That is going to equal C22, and that's going to be 7. Subtraction is conducted very similarly. Again, you have to have them be the same dimensions, so you can add a 2 by 2 to a 2 by 2, you can add a 2 by 3 to a 2 by 3, but you can't add a 2 by 2 and a 2 by 3. So here, we'll again take A11, and this time we'll subtract B11, and it will result in -1 and C11. Or if we go down to A22, which is -3, subtract 10, the result will be -13, or C22. Now, the first part of multiplication we're going to introduce is multiplication by a scalar. This is the most simple form of multiplication in matrix algebra, where a scalar is defined as a single value. So to multiply a matrix by a single value, you just multiply each element of the matrix by that value. So the matrix is 5, 7, 11, and 6. I'll first multiply 3 by 5, and that will get me my score that I have over here of 15. If I multiply 3 by 6, that's going to result in 18. You would also do 3 by 7 to get 21, and 3 by 11 to get the 33. So that you multiply each of the 4 elements by that scalar, and that results in the B matrix that we have here. To multiply a matrice by another matrice, that's a more complex step, and one of the first things we have to know is that matrices have to be conformable. Now, a conformable matrix has the same internal dimensions, what we see here, a 2 by 3 and a 3 by 4. That is conformable. In this other example that we have, the 2 by 4 and the 3 by 2, notice that this 4 and 3 are not equal or identical internal dimensions. We could not multiply a 2 by 4 and a 3 by 2. So you can't do the bottom one, but you can multiply a 2 by 3 and a 3 by 4. The resulting dimensions will be based on the external dimensions of the conformable matrix. So when you multiply a 2 by 3 and a 3 by 4, we're going to use these external dimensions, 2 and 4, and the resulting matrix is going to be a 2 by 4 matrix. And let's see what that looks like. So when you multiply a matrix, it's done by multiply rows and sum down columns. That's a little bit confusing, but again, we still have that rows by columns, and if you take each of these steps, hopefully you'll be able to follow. First, we're going to take the 3 and multiply it by the 4. So I multiply by a row, and then I'm going to sum down a column, where I'm going to take the 2 and multiply by the 2. So this first element will be the 3 by 4 plus 2 by 2, which results in 16. Then I'm going to do the second part, 3 by 1, so that's multiplying by rows, 2 by 6, that's multiplying by another row, and then we result in summing up the columns. 3 by 1 gives me 3, plus 12 gives me the 15 that I result in here. If you need a chance, this is a bit of a harder calculation. Pause this, try to practice it for yourself. There's an opportunity to check your understanding later in this. One of the notes you have to know about multiplication is that it is associative, just like you're used to normal multiplication. So if you wanted to multiply matrix A by C by A by B by C, you could multiply A by B first and then multiply C, or you can multiply B by C first and then multiply by A, and the results will all be the same. The resulting matrix C will all be the same. However, it is not commutative. That means multiplying A times B is not the same thing as multiplying B times A. And the reason that that could be also a big issue is that when you reverse the matrices from A to B times A, they might no longer be conformable. So if matrix A was a 2 by 4 and matrix B was a 4 by 6, if I multiplied that, that would result in a 2 by 6 matrix. However, if I were to switch this round to be a 4 by 6, or 4 by 6, and multiply that by a 2 by 4, my internal dimensions are no longer conformable, and I wouldn't be able to calculate that calculation at all. So those two things are important to recognize. Notice in this first example I gave here up here in associative, the order stays the same. A and B, then C, never changes. Now the last part of this video too will be going over what a determinant is. A determinant is a single number that represents a square matrix, and it can only be calculated for a square matrix. That means a matrix that has both dimensions to be identical, 2 by 2, 3 by 3, 4 by 4, and so on. A determinant is denoted by the matrix bracketed with absolute bars. For a 2 by 2 matrix, it's calculated by multiplying the elements of the and this should be principal diagonal, or multiplying the elements of each diagonal and subtracting the value of the off diagonal from the principal diagonal. That sounds a little bit confusing, but let's actually try it. First, you're going to multiply 2 by 3, and that's what we have right here. Then you're going to multiply 7 by 4, and that's what we have here. And we take the principal diagonal and subtract the off diagonal. So I have 2 by 3, which is the principal diagonal. 2 by 3 gives me the multiplication of the principal diagonal. The 7 by 4 gives me the multiplication of the off diagonal. I subtract the 28 from 6, and that's what gives me negative 22. There are many applications for determinant in statistics. One of the really basic ones that we've already seen is it actually is representative of a unexplained variance, and you can see here at the bottom why. In the bottom, I have an R matrix where the correlation, and we have the principal diagonal at 1.0, and the correlation equals 0.599. If I were to multiply 1 by itself for the principal diagonal, I'd have 1 by 1. If I were to multiply 0.599 by itself, I would have the off diagonal multiplication over here, 0.599. Well, 1 by 1 is just going to give me 1, so that's fine. 0.599 is the same thing as essentially saying R squared. So I have 1, which is akin to 100%, minus R squared, which is our percentage of explained variability. So if we do 100% minus explained variability, what we have left is percentage that is unexplained over here. So that's this first application of a determinant. A determinant of a variance-covariance matrix, which is something we're going to look at later this semester, is equal to generalist variance-covariance for all variables. You're going to see a variance-covariance matrix in a lot of our work that we're going to do later in the semester with factorial novas, MANOVAs, and so on. A determinant is also going to be used in the calculation of Wilks lambda, which is the test statistic for a MANOVA. As opposed to using an F ratio, in MANOVA we use Wilks lambda, where it's the determinant of within variance over the determinant of total variance. And that's how we're going to calculate our significance test in MANOVA. Well, that takes us to the end of video 2. In the last video, we're going to go over division, which is also called taking the inverse of a matrix, and that's where we'll finish off for these videos to prepare you for class.